All right, starting right out the gate, properties of gases. This is going to be the first chapter in the UAA Chemistry 411 course, Biophysical Chemistry. Just so everyone's on the same page, Biophysical Chemistry is a course targeting Calc 1 appropriate examples of first semester physical chemistry, which typically revolves around equilibrium processes, kinetics, and thermodynamics from a chemical perspective, and this will be in the context, when possible, of biological examples. So on that note, a lot of the things that we're going to talk about in this class are quite familiar from 100-level chemistry. You'll have seen a lot of this in second semester and first semester general chemistry, and I believe, well, I'm sure that not only will it be familiar, but will elaborate significantly on a lot of the topics that you're familiar with, and you'll get a much deeper understanding on these concepts. So on that note, moving along. So, properties of gases, we've got to start gases with the ideal gas law. And I'm going to refer to it as the ideal gas law, even though in this text, the author separates what he refers to as the perfect gas equation from the ideal gas equation. I'm comfortable with them being interchangeable in the context of this class. And because of that, I'm going to habitually refer to it as the ideal gas law. So the ideal gas law is something everyone in this class has seen, but it's worth doing a quick review and getting into a little bit more detail with it. So what's really compelling about the ideal gas law is it's an equation of state. And what that means is that for any substance, we can define the state of that substance by giving and assigning values of the following properties. And those following properties include volume, pressure, temperature, and the amount. But what's really compelling about that, you're like, of course, Dr. Miguel, we understand volume, pressure, temperature, and amount, is that these four quantities are not independent of one another. Meaning, if you have a sample of, say, 0.55 moles of water in a volume of 100 milliliters at 100 kilopascals and 500 Kelvin, you can't have that. It's found experimentally that that state does not exist. So if we select the amount of volume and temperature of 0.55 moles and volume of 100 milliliters and the temperature of 500 Kelvin, it turns out that can only exist at a single pressure, and that pressure is 23 megapascals, a very, very high pressure system. And this is true of all substances, but the pressure in general will be different for each one. So the experimental generalization of this is as follows. Here, let me change the color up here real fast. There we go. That means that pressure is equal to some function, which includes the molar quantity, the volume, and the temperature. And this expression tells us that the pressure is some function of the amount, volume, and temperature. And if we know these three variables and we know the rest of the function, the pressure can only have a single value. So the equation of state of a low pressure gas was really among one of the first things that was determined in physical chemistry. It turns out we don't have equations of state for most substances, but for gases, we do. And this work was carried out by Robert Boyle, along with a number of his colleagues. And getting right to the gist of it, something familiar, PV equals nRT, or PUVnert. And that is just a statement that the pressure of an ideal gas times the volume equals the amount of the gas, the molar quantity, times the ideal gas constant, R, which is the constant which ties it all together, times the temperature in Kelvin. So a hypothetical substance that obeys PV equals nRT at all pressures is an ideal gas. And from what has just been said, actual gases or real gases don't necessarily agree with ideal gases, particularly at very high pressures where they have increased incident of collision with one another and association. So we're going to talk about this exception and how real gases diverge in behavior from ideal gases. But we're going to do that in a little bit. For now, just understand that under normal low pressure conditions that we experience most gases, real gases actually behave in a fairly ideal fashion. So as a model, PV equals nRT is quite appropriate. So let's look at some of the ways we can utilize the ideal gas law, or PV equals nRT, to solve some problems. And one of the ways we can use it is if we're holding certain components of PV equals nRT constant, we can use simplifications. And the first simplification is going to be Boyle's law. So Boyle's law just states that at a constant temperature, the pressure of a fixed amount of gas is inversely proportional to the volume. And how we come up with that is if PV equals nRT, and we have a constant temperature, so it's constant, it does not change in the system, and the pressure, and we have a fixed amount, N, R is a constant, R, that means that if we rearrange this, P is going to have to be inversely proportional to 1 over V. So this is what we're seeing in Boyle's law. And let's take a look at figure 1.1 off to the side here. On the y-axis of 1.1 we have pressure. On the x-axis we have volume. And then what we see is a sequence of isotherms. And what's really neat about this figure is that as we have increasing temperature moving along this arrow, the isotherms are actually color-coded, with blue being the coolest and red being the hottest. So for each individual temperature, there is a unique isotherm relating pressure to volume for any given quantity, as related by this constant R. And what's important to take away, though, is this inverse proportionality generally regardless of the temperature. Now, if we take a look over to figure 1.2, once again we have pressure, but instead of volume we have inverse volume, or 1 over V. And this is because a good test of Boyle's law is to plot the pressure against the inverse of the volume at a constant temperature. And what you should see with this is a straight line because of this relationship we see with Boyle's law. And that's what we see with the blue trend line pressure versus 1 over V, is this ideal gas behavior. Now next to that we see an observed sequence of data points for a real gas. And what I want you to take a look at here is that it doesn't behave ideally over the entire range of data. Notice as the pressure increases and the volume decreases, meaning 1 over V is a higher component, you see a larger divergence in the observed quantities versus the ideal quantities. However, under lower pressure systems, you have pretty darn good adherence to the model. And this goes back to what we were just discussing in the previous slide. Now, moving along, we have Charles's law, which is another approximation of PV equals nRT. And Charles's law just simply states that at constant pressure, the volume of a fixed amount of gas varies linearly with the temperature, or V is proportional to T. And that makes sense because if we have PV equals nRT and we have a fixed amount of gas, N is constant, and pressure is constant, and R is inherently a constant, then V must be proportional to T. So that's the derivation of Charles' law. Now, another approximation is going to be Avogadro's law, and that states that at a given temperature and pressure, equal volumes of a gas contain the same number of molecules. And that's an interesting way to say that the volume of a gas is proportional to the amount of the gas. Meaning if you hold the pressure and the temperature constant, and you don't let those change, that as you increase the amount of gas, the volume must increase proportionately. And this takes us to a very interesting concept of the molar volume of gas. And what we'll see is that the molar volume of gas is actually the same for all ideal gases, regardless of their molecular size. And that real gases behave very similarly to this under normal pressures and temperatures. So let's take a look at this concept of a molar volume. Molar volume is V sub n. And what that is it's the volume of a sample that is occupied by a particular amount of substance in moles. So the volume of gas over the moles of gas equals the molar volume of the gas. And if we're using PV equals nRT, we can rearrange PV equals nRT to solve for V over N or slash V sub M. And when we do that, we see that the molar volume is equal to R times T over P, or the ideal gas constant times the temperature in Kelvin over the pressure. And when we solve for this at standard temperature pressure, which is 0 degrees Celsius and 1 atmosphere, we see that an ideal gas occupies a particular constant volume, and that real gases, ammonia, argon, carbon dioxide, nitrogen, oxygen, hydrogen, helium, all deviate just slightly. They hover right around the same quantity. So under standard temperature and pressure, all gases have very nearly the same molar volume as predicted by the ideal gas law. So how do we use the ideal gas law? I'm going to move a little faster this because in general chemistry we did a fair bit of this, and I don't want to linger here too long. But we'll just do one quick example and talk about the strategy of problem solving. The first problem, predicting the pressure of a sample of gas using PV equals nRT. A chemist is investigating the conversion of atmospheric nitrogen to usable form by bacteria that inhabits the root systems of certain legumes and needs to know the pressure in kilopascals exerted by 1.25 grams of nitrogen gas in a flask of volume 250 milliliters at 20 degrees Celsius. So what do? Well, first we take PV equals nRT and we identify which value we're trying to figure out, and that's going to be the pressure. So we're going to solve PV equals nRT here by dividing both sides by volume, giving us the new working relationship, pressure equals nRT over V. So once we have this, we have to work with what we were given so that we can put them into units that we can substitute that align with the units with our ideal gas law constant, in this case 8.314 joules per Kelvin per mole. So things have to be in joules, Kelvin, and moles, right? So what does that look like? Well, we can obtain the molar mass by taking the mass and using the molar mass of nitrogen gas. That's pretty straightforward. For the temperature, we need to convert to absolute or Kelvin. So we need to add 273.15 to the temperature that we were given in Celsius. And we need to select R, the appropriate R, which is 8.314 joules per Kelvin per unit mole. And of course, volumes in liters, so 250 centimeters cubed is 250 milliliters, which is 0.25 liters. These are all things that we did routinely in 100-level chemistry. And once we have all these values, we can plug this right into pressure equals nRT over V and plug and chug. And we can get the solution in pascals in this particular case because joules per meter cubed equals pascals. We have the ability at this stage in our education to move between units. So pretty straightforward. Now, if you're interested in testing this out, or you can just jump into homework, feel free to look at these little quick self-evaluations. Do you have comfort moving about this type of problem-solving strategy? So, moving along, slowly adding complexity. Let's talk about mixtures of gases, in particular partial pressures. So, Dalton's law states that a pressure exerted by a mixture of ideal gases is the sum of the pressures that each gas would exert if it were alone in the container at the same temperature. Meaning if you take a mixture of gases and you magically took all of the gases out except for one, the pressure that single component contributed would not change. And as you add them in sequentially, they each have their own unique contribution to the total pressure. And we can express this by the term the total pressure, or P, and you can call this, I will often say P total equals PA plus PB plus PC, etc. But for the book, they don't say P total, they just say pressure as the total pressure equals P sub A plus P sub B. And component A is giving you pressure A, component B is giving you pressure B. And what we see here from figure 1.4 is the partial pressure P sub A of a perfect gas A is the pressure the gas would exert if it occupied the container alone. The partial pressure P sub B of perfect gas B is the pressure that it would exert in a container alone. And if you put the same quantity of gases under the same conditions into a single container, whereas A gives you 5 kilopascals and B gives you independently 20 kilopascals, when you put them together, you'll have 25 kilopascals. And this gives you the ability to do some problem solving in which, if you know a total pressure and you know molar quantities of gas, you can assign pressures to those individual components. So also something we did at 100 level, but something we need to keep in mind when we do some more complex problem solving down the road. Now, let's take a look at what this might look like. Let's take a look at the figure 1.5 here. And this is just a representation of what mole fractions look like. Why are we suddenly looking at mole fractions? Well, because if the pressure is proportional to the amount, then if the pressure is simply a sum of partial pressures, we can express those partial pressures as mole fractions. So for any real gas, or ideal gas in a mixture, the partial pressure, P sub J, of gas J is defined as the following. P sub J equals the mole fraction of J, X sub J, times the total pressure. Meaning, if you know the mole fraction and you know the total pressure, you can calculate the partial pressure, P sub J, for any component. In a mixture that contains N sub A molecules of component A and N sub B components of molecule B, and so on. So you have all these different potential components, A, B, C, etc. The mole fraction of J, where J is A, B, C, etc., looks like the following. And this is really just another way we can get at partial quantities. So if you know the total amount of molecules in the mixture and you know the amount of molecules of any particular component, A, B, C, within that mixture, you can calculate the mole fraction of that, a particular component, X sub J. And where mole fractions are unitless, because the unit mole in the numerator and the denominator cancel one another, For a binary mixture, one that consists of two species, this general expression becomes the following, where if you only have two species, the mole fraction of A equals the number of moles of A over the number of moles of A plus the number of moles of B. And conversely, the mole fraction of B is the number of moles of B over the sum of the number of moles of A plus B. So another way to look at this is if the total is always 1 or 100%, the mole fraction of A plus the mole fraction of B in a two-component mixture has to be equal to 1. This makes sense. Now, if everything's in equal ratios, then mole fraction of A has to be 1/2, mole fraction of B has to be 1/2. And when we're looking at mole fractions, this illustration off to the side, coming back to it finally, is a pretty darn good representation, where on top we have component A in yellow, component B in green. And you can visually see, even though it's not homogeneously distributed, that there's more of A than B visually. And that's represented where the mole fraction of A is 0.708. The mole fraction of B in this particular case is 0.292, and the sum of these is equal to 1. Another example, if we look further down, you can see in this particular example, there's substantially more component B than component A. You can see that visually immediately, even though it's not homogeneous. In this particular case, A occupies 0.229 parts of 1, and B occupies 0.771 parts of 1, and together they sum 1. Now, in continuing our discussion on partial pressures and mixtures of gases, for a mixture of perfect gases or ideal gases, we can identify the partial pressure of J with the contribution that J makes to the total pressure. So if we introduce P equals nRT over V into the previous equation, 1.7, we get the following right here. So remember, the partial pressure J of component J is equal to the mole fraction of J times the total pressure. If we substitute nRT over V for pressure here, we get the mole fraction of component J is equal to nRT over V. We can pull n sub J out of the relationship and over like this, and then just rearrange it so it looks like this. And what we see is that the partial pressure of component J is equal to the number of moles of J, specifically, times RT over V. So this is a really slick way to combine PV equals nRT with molar quantities to get to partial pressures without having to actually calculate the mole fraction first. Now, let's take a little bit of a different path. We're going to look at the rationale of pressure from the kinetic model, and then we're going to elaborate on this substantially. So the kinetic model of gas is based on 3 assumptions. And if you just kind of scan your eyes over real fast to figure 1.6, you see this diagram where you have a box where you have these gas molecules bouncing around. And those collisions are really going to be the rationale for pressure. Now, we have to think of the mass of the object causing the collision, the velocity, the distribution of velocities, the a variety of factors that we're going to get into in substantially more detail. But for now, think about all those collisions collectively leading to what we think of classically as a uniform pressure of a gas being exerted at any particular quantity, temperature, and volume, which affect that. And we'll be able to rationalize a lot of the components of PV equals nRT in the ideal gas law through this kinetic gas model. So, the assumptions. 1, a gas consists of molecules in ceaseless random motion. 2, the size of the molecule is negligible in the sense that their diameter is much, much smaller than the average distance traveled between collisions. And 3, the molecules do not interact except for during collisions, meaning that this model is assuming there is no intramolecular forces or interatomic forces, either attractive or repulsive, taking place, only collisions. So the assumption is that the molecules do not interact unless they are in contact, implying that the potential energy of the molecules, their energy due to position, is independent of their separation and may be set equal to 0. Super important. The total energy of a sample of gas is therefore the sum of the kinetic energies of all of the molecules present in it. It follows that the faster the molecules are traveling, hence the greater kinetic energy, the greater total energy of the gas. So, how does this general model apply mathematically? Let's take a look at the pressure of a gas according to this kinetic model. So the kinetic model accounts for the steady pressure exerted by a gas in terms of the collisions molecules make with the walls of the container. So when you think about the gas exerting pressure, it's about those collisions exerted on the walls of the container itself that we think of classically as pressure. Each impact gives rise to a brief force on the wall, but as billions of collisions take place every second, the wall experiences a virtually constant force. Therefore, the gas exerts what appears to be a steady pressure for all intents and purposes. So on the basis of this, the pressure exerted by a gas of molar mass m in volume V is defined by equation 1.9. Pressure equals the number of moles, N, times the molar mass, m, times c, which is the root mean squared speed, we'll get into that, squared, divided by 3 times the volume V. So you're like, wait, hold on, what's going on with c here? C is the root mean squared speed, or RMS speed of the molecules, and this quantity is defined as the square root of the speed value of the squares of the speeds v of the molecules. So that means for a sample consisting of n molecules with speeds v1, v2, all the way through vn, we square each speed, add the speeds together, those squares together, divide by the total number of molecules, n, and then once we've done that, take the square root, and that's the root mean squared value, c, which is a description of a mean speed of the population of gas molecules, because they're not going to be homogeneous. So the RMS speed might at first sight seem to be a rather peculiar measure of the means of speeds of molecules, but the significance becomes clear when we make use of the fact that the kinetic energy of a molecule of mass m traveling at a speed v equals kinetic energy equals 1/2 mv squared, which means that the kinetic energy, E sub k, is the average of this quantity, or 1/2 mc squared. So it follows from the relationship 1/2 mc squared equals kinetic energy that the root mean square speed c equals 2 times the kinetic energy of the sample of gas over m in the square root of that quantity, where m is the mass. So therefore, wherever c appears, you can think of it as a measure of mean kinetic energy of the molecules of gas, which is a really, really slick way to bring kinetic energy to our first term describing pressure. So the RMS speed is quite close in value to another and more easily visualized measure of molecular speeds, and that's just the mean speed, which is this term C with a little line over the top of it. And that's just going to be a literal mean where you sum the population and divide by n. But even though it's easier to recognize, I think we all are mathematically sophisticated enough to look at root mean squared as a mechanism. So for samples consisting of really large number of molecules, the mean speed is actually going to be slightly smaller than the RMS speed, and that precise relationship is actually quantifiable here, where the mean speed is actually equal to 8 over 3 pi, the square root of 8 over 3 pi, and where C is actually approximately equal to 0.921 C. So it's, and I'm not going to put you guys through that, but just recognize that they are mathematically related and interconvertible. So if you were given one, you can find the other in the absence of other information. So what we were just looking at was the pressure of gas according to kinetic model. Let's take a look at the average speeds of gas molecules. So suppose that the expression for pressure times volume derived from the kinetic model is indeed the equation of state of a perfect gas. That being so, we can equate the expression on the right of equation 1.14 to nRT. So if PV equals nRT, then PV also can equal 1/3 nmc squared. Well, that's quite interesting, which means that we can pull PV out, set nRT and 1/3 nmc squared to be equal to each other, and then we get some inherent cancellation where n's cancel, right? And we get a new relationship, 1/3 mc squared, which is molar mass, root mean squared, equals RT. So the usefulness or utility of this expression is that we can rearrange it into a formula for RMS speed of gas molecules at any temperature. So by solving for C, we can find RMS for any population of gas molecules by looking at the square root of 3RT over m. Super slick. So we have a variety of tools in our tool belt now to look at pressure exerted by gas, speeds exerted by gas, ways to evaluate kinetic energy of a population of gas molecules by looking at RMS speed. But of course, we have to make it a little bit more nuanced than that, right? Because the mathematical expression that tells us the fraction of molecules that have a particular speed at any instant is going to be called a distribution of molecular speeds. And populations of gas molecules aren't going to be uniform in speed. So we have to be able to evaluate how the population is behaving. So a distribution might tell us that at 20 degrees Celsius, 19 out of 1,000 oxygen molecules have a speed in the range between 300 and 310 meters per second, and that 21 of 1,000 of them have a speed between 400 and 410 meters per second, and so on. The precise form of this distribution was worked out by James Clerk Maxwell towards the ends of the 19th century, and this expression is known as the Maxwell distribution of speeds. So according to Maxwell, the fraction f of molecules that have a speed in a narrow range between s and s plus delta s, for example, this could be 300 meters per second and 310 meters per second, corresponding to s of 300 meters per second and delta s of 10 meters per second, being the delta between 300 and 310, is the following. Where we have this function, f equals this function of s, delta s, where the function of s equals 4 pi times the quantity m over 2 pi RT to 3 halves power. This is getting, like, everyone right now, don't worry, we're going to break this down into components, don't sweat too hard, times s squared times e minus the exponent ms squared over 2rt. So let's talk about first the shapes of exponential functions in a quick review before we get into what this looks like in the subsequent pages. And we're going to look at two different types of exponent functions. The first here and the second here. Notice that in this particular difference, one of the exponents is not squared and the other one, it is squared. And the difference is going to be we're going to have an exponential function and we're going to have a Gaussian function. So an exponential function is a function of the form e to the power of minus ax. And it starts off at 1 when x equals 0 and decays towards 0. And when it reaches x, which it reaches as x approaches infinity. So this function approaches 0 more rapidly as a increases because it accelerates the process to add that to the exponent. And we see that in figure 1.7 here, where in the green line here, it approaches infinity and approaches 0 in a simple exponential function. And then we have the Gaussian function, and this is the function in the form e to negative ax squared, and it also starts out at 1, them start down at the same point when x equals 0, and decays to 0 as x increases. However, its decay is initially slower and then plunges down to 0 more rapidly than the exponential function. And additionally, it's mirrored, or it doesn't approach infinity on the opposite side. So now that we've covered this, let's consider the following for that hideous equation we looked at. Because f is going to be proportional to a range of speeds, delta s, defining that range, we see that the fraction in the range delta s increases in proportion to the width of the range. So if at any given speed we double the range of interest, but are still unsure that it's narrow, then the fraction of molecules in that range doubles too. Super important. So the equation included a decaying function, and this term, function of s equals 4 pi times the quantity m over 2 pi rt raised to 3/2 power. This decaying exponential function is circled in red right here. Its presence implies that the fraction of molecules with very high speeds are going to be very small, because e to the negative x squared becomes very small when x squared is large. So as x gets larger, that fraction is going to become smaller and smaller and smaller, meaning the fraction of molecules which are going to have very high excitement is going to decrease under those conditions. So the factor m over 2rt multiplying s squared in the exponent, which we see here, in the exponent specifically, is large when the molar mass m is large, which makes sense because that's what we're starting with. So the exponential factor goes most rapidly towards 0 when m is large. That tells us that heavy molecules are unlikely to be found with very high speeds, and intuitively that makes sense. From just a pure Newtonian standpoint, you don't expect to see, with a certain amount of energy available to excite a system, that heavy molecules will be excited at very high speeds compared to smaller molecules or smaller objects. And the opposite's true when temperature T is high. Then the factor m over 2rt in the exponent is small, so the exponential factor falls towards 0 relatively slowly as s increases. This tells us that at high temperatures, a greater fraction of the molecules can be expected to have high speeds than at low temperatures. And that makes sense too, because at high temperatures, you have more energy available, and you would expect a higher fraction of molecules to be excited to higher speeds than you would at lower temperatures. That's a pretty intuitive outcome of that function. So for the factor s squared that we see here, this factor multiplies the exponential. This factor goes to 0 as s goes to 0. So the fraction of molecules with very low speeds will also be very small. And then finally, the remaining factors, the term circled here, simply ensure that we add together the fractions over the entire range of speeds with 0 to infinity, and then we get 1 as a whole. So this is a relatively large equation with a lot going on, but if you break it down into its components, the implications of what these components mean are quite rational when you think about it. So what's this look like in terms of these Maxwell distributions? These are two really good diagrams, figures 1.8 and 1.9. Starting with figure 1.8, on the y-axis we look at the number of molecules, and on the x-axis we have speed. And we see this relationship, number of molecules in a population versus speed, ranging over temperatures, starting with low temperatures with the green curves and ranging to high temperatures with the red curves. And what you see is this Maxwell distribution of speeds and its variation with temperature. So note the broadening of the distribution and the shift in the RMS speed to higher values as temperature increases. So higher temperature increases the speeds of the molecules, but also creates a broader distribution of speeds than low temperatures. And when we look at figure 1.9, we see on the y-axis number of molecules in a population again versus speed, but instead of looking at temperature variation, we're looking at the effect of heavy molecules versus light molecules, with green curves being heavy molecules trending towards lighter and lighter molecules in red. And we see also in this case that Maxwell distribution of speeds depends on the molar mass of the molecules, where molecules of low molecular mass have a broad spread of speeds, and a significant fraction may be found traveling much faster than the RMS speed. The distribution is much narrower for the heavier molecules, and most of them travel speeds closer to RMS value. So that's it for Maxwell's distribution. We're going to move on to the concepts of diffusion and effusion. But I think I'm going to cut this off here and upload this first video, make it a little bit digestible. I think at this point everyone's pretty saturated. And so what I think the best approach is at this point is stop here, jump into some of the homework problems, and tackle the homework problems that are appropriate for the lecture content. Let those topics work through and then come back, pick up diffusion and effusion and the following topics in subsequent lecture, and we'll finish up the chapter in about another 45 to an hour.